Right now, we're pushing the boundaries beyond the 7 nanometer technology node. So the size of our features are in, the tens of nanometers scale.
Dr. Rudy Wojtecki always knew that he wanted to work for IBM. One thing led to another, and that's exactly what he's doing today, blazing new trails at their Almaden Research and Innovation Laboratory. In this Season 2 episode of Bringing Chemistry to Life, we speak with another member of Chemical and Engineering News's 2020 Talented 12 about their work and trends in their field. I'm your host, Dr. Paolo Braiuca from Thermo Fisher Scientific. We began by asking Dr. Wojtecki about where he found his original scientific inspiration.
I really gravitated towards chemistry and synthesis in particular because it was a way of manipulating matter to build useful molecules, useful materials in general. So it's part of that creative process that I really enjoy, exploiting, science and that understanding of the world around you.
IBM is not the first place you would think of for a chemist, right? And yet chemistry is your main background. But of course, you need to cross-link your chemical skills with, the engineering skills that go into making these electronic devices and all the technology that is behind. And how much would you say that your general interest in science and you being a curious person is been important so far for yourself?
I think that's a very critical mindset to have going into working at some place like a research outfit like IBM Research in general, because it helps you engage with other people and in very different project areas, because there may be some part of those projects that you may not have thought you could contribute to it, but looking at it through a different perspective and providing some additional value through that perspective is something that I think helps you broaden how you can impact technology in general. So, I've been engaged in a lot of different project areas within IBM. Some of them are in electronic devices. Some of them are in fundamental studies of chemistry. And in that technology space, there's so many different ways you can apply that skill set of chemistry to different problems, from fabricating devices to packaging them, to making your conventional transistor-based devices, to making some of the more exploratory devices involving things like superconductors or maybe unique material sets. So having that curiosity in general as a fundamental passion is something that really is well suited for a research environment like this. The link between chemistry and polymer chemistry at that in IBM, even as an undergraduate, I didn't really make that connection. But in graduate school, my mentor, my research mentor, Stuart Rowan, he worked for the same group as who became my first manager, Al Nelson. And at that point, you could see how chemistry played such a significant role in the microelectronics industry, where in Almaden in particular, it was the birthplace of the chemically amplified resist. And this is what really enabled Moore's Law and enabled us to reach the technology nodes that we're at right now from the use of those type of polymeric responsive materials.
So the opportunity of fulfilling your dream of joining IBM came through the connection between your PhD mentor and basically his network, right? So eventually you made it. So was that an obvious move after you completed your PhD and your graduate studies?
No, actually, I was looking at some other postdoc opportunities to work in things like drug delivery and producing macromolecular architectures to do that. And this opportunity at IBM came about because there were two people that retired at Almaden. And it just so happened that my skill set in my research project at Case Western was in making some very complex polymeric architectures that required some very advanced NMR techniques like diffusion NMR, fluorine carbon, 2D NMR, and so it was a really good fit given my skill set. And this opportunity that came about was an associate engineer, and most people that want to be research staff members generally go through a postdoc position. So it was a little bit of an unconventional way to get into IBM and then to go from there.
So is it true that you worked on a number of side projects as you were, in your initial position in the NMR team, and this sort of involvement in these side projects was actually instrumental in your career development inside the organization?
Absolutely. This was a significant goal of mine to become a part of this research organization, given its very distinguished history and all of the amazing technology that has come out of the organization and the company in general. And the people at Almaden have that scientific reputation. So as I joined, of course, I want to work with some of the world's leading scientists in polymeric synthesis and developing materials for electronics. And so being that very curious person, I talked to people and tried to leverage the skill set of NMR characterization and using some of these techniques like diffusion NMR to advance their research and to help them characterize some of the materials that they've been making. And that link was very valuable. What's really unique about the IBM research in Almaden is there's this collegial atmosphere here where if somebody needs help, people tend to help them, right? Or if somebody has questions, there's a very collaborative environment here. And I think that's particularly unique because the other end of the spectrum is siloing individual projects, not talking to one another. But that's the exact opposite of what I experienced here at Almaden. It really is a research community.
And I guess being curious and able to work across disciplines and understanding problems or being interested in problems is what makes this involvement, right, with a broader research community at the sites easier.
When it comes to electronic hardware, as you said, it's a very interdisciplinary field. My background in polymer chemistry and synthesis may be able to help address one part of a much larger problem, but you have to have teams of people. You have to have groups of people that have different perspectives, whether it's an electrical engineer or a designer or somebody that's heavily interested in or very well equipped to do things like chemical vapor deposition. So it really takes all of those different perspectives to move things along. And so in order to do that, you go much further working on those teams rather than trying to work alone.
I'd like to go down into some of the details of what you and your team are pursuing, and what can you tell us about the work you're leading at the moment at IBM, and what's the directions, and how do you apply your chemical knowledge to the technology problems that IBM is addressing?
There's one focal point that we're working on right now, and that is in area selective depositions. It's a very simple goal. And that is, if you envision a pattern surface, and let's just, for the sake of this discussion, we just say it's a planar surface. And you may have lines of a metal, and spaced in between that metal, you'll have dielectric, and that may be something like silicon. It could be silicon nitride, silicon oxycarbide, things along those lines. So with that pre-pattern, the idea is you want to expose that to a process that would then selectively grow a film on one of those surfaces. So you want to create topography on your surface. So you start with a coplanar surface, you want to deposit a dielectric, and that creates maybe some bumps on the surface. And that's actually particularly useful in advanced technology nodes. And there are other applications here you can also do. For instance, you can put a metal selectively on a metal. All of these are very useful processes if you're going to actually build a device or extend your ability to make devices at smaller and smaller feature scales. And so that's the overall problem that we're trying to address. And again, coming at this from the perspective of applying chemistry and synthetic development to that, this field has been established in the last 15 years by some amazing pioneers that have demonstrated that type of work. In the literature, we observed that there were maybe a handful of organic molecules that were used to achieve that. And that small number of molecules made us wonder, well, maybe we could synthesize a better version of these, or ones that achieve more selective growth, or being able to deposit films at higher temperatures, or reducing things like lateral overgrowth if it's an isotropic film formation. We applied that lens, and we're able to show that with the introduction of things like cross-linking groups, we could reduce defectivity of that type of process. And maybe it's useful to say that if you're working in developing a technology for electronics, the bar is incredibly high for you to make something or implement one of these processes in a technology that would go into high volume manufacturing.
And I guess it gets more and more challenging as you squeeze more transistors into the same surface, right? And so the distances become smaller and smaller in your pattern. So your level of precision needs to actually increase while you keep the defectivity very low. What kind of chemistries you leverage for growing these films on semiconductor types of surfaces or metal type of surfaces? Can you give us some examples?
For an area selective deposition, you typically start with these pre-patterned surfaces. And as I said, you generally start with a metal versus a dielectric. So if you want to have an organic material selectively stick on one of those surfaces, you have to exploit some type of surface chemistry that may only happen between a metal and an organic, and doesn't happen between a dielectric like silicon nitride, silicon oxycarbide, and that organic material. So in graduate school, I worked on developing a synthetic method for making mechanically interlocked rings. And what we did is we used a templated synthetic approach that involved metal ligand interactions. And in that respect, we exploited things like nitrogen-containing ligands that bound in a very selective manner with a metal like zinc. We've done iron, we've done a variety of other metals, but that supramolecular interaction between a metal and an organic is the same thing that we exploit for this area selective deposition. So the ligand may not be this bulky organic. It may be as simple as something that looks like a surfactant, where you may have a phosphonic acid at one end of the molecule, and at the other end you have some reactive groups or some long chain. And that interaction between the ligand and your metal, you can exploit that to have your organic selectively stick on those surfaces. And it's that type of supramolecular metal ligand interaction that we exploit to achieve this type of deposition.
What kind of selectivity or spatial resolution you can achieve with this sort of chemistry? Is it in a nanometer, sub-nanometer kind of scale?
It all depends on your incoming structure. Right now, we're pushing the boundaries beyond the 7 nanometer technology node. So the size of our features are in the tens of nanometers scales. But that isn't necessarily a fundamental limitation for this process. I haven't pushed it beyond those structures that we typically get from our colleagues and collaborators at IBM Semiconductor Research. So There are groups at Almaden that have the capabilities of moving atoms on a surface and being able to look at atomic resolution, but we haven't gone beyond these incoming structures at this point. So, but I don't think there's necessarily an upper boundary or maybe a lower boundary in terms of the size scale for these.
We hope you're enjoying this episode of Bringing Chemistry to Life. Stay tuned at the end of the episode for information on how to access content recommendations from our guests, as well as information on how to request your free Bringing Chemistry to Life t-shirt. And now back to our conversation. You mentioned lens, and this makes me think about lithography again. During last year's Future Festival, you described the use of additive lithography as a sort of an additional tool, right, to improve selectivity on the films you grow. Can you describe how that works?
Yeah, certainly, and maybe again to put this in context for the overall trends that you can observe in semiconductor research in general, you can observe that as you push resolution, your resists tend to get thinner and thinner. If you compare using something like a resist for in printing with that in 248 nanometer exposures versus extreme ultraviolet, the thickness of your resists are very different, much thinner when they come to the EUV resist if you're pushing resolution limits. And you start to see other types of materials for those smaller feature sizes and printing in EUV come online and start to be implemented, like inorganic resists, for instance. And those are still quite thin. So where do you go from there? And in a conventional lithography sense, you can envision, I can certainly create a monolayer of an organic material at a surface, but if I were to expose that, what would I do with it? And your ability to develop, and typically with a resist, what you'll do is you'll expose it, and there'll be some type of liquid developer that you use to remove portions of the film, unexposed portions of the film in one tone, and in another, the exposed areas. And that's what allows you to print those features. So if you have a monolayer of material, and even if you were to remove portions of that, well, what do you do with that? If you try and do pattern transfer through some etching process, that organic material etches very quickly, and it'd be very difficult to get a very nice pattern into silicon as a result of that. So the other thing you can do with that, because these are organic materials, tend to have no dangling bonds that would nucleate different types of ALD growth, you can use those type of monolayers as a way to selectively grow your film in an area. So this is to contrast a conventional way of going about lithography, to challenge this idea that instead of subtracting and then etching, well, maybe you can do an exposure and then just grow a film where you want it. Another point to this, or another part to this idea, was this idea of additive lithography. If you have the correct type of molecules, and if you start with a pre-patterned surface, well, now you have a type of photoactive material that will selectively adhere to a metal portion of your film. And so it gives you another tool set to allow you to have a self-aligned type of component to your resist. And this idea of self-aligning touches on one of the immense technical challenges as you push that critical resolution, or as you start to try and make even smaller feature sizes than what we can do today. And again, if you think about how a device is made, it's layer by layer by layer by layer, right? Again, starting with the front end to the middle of the line. And each one of those steps requires an alignment process. So if you're using lithography to align to that front end so that you can put contacts to your devices, you better have something that is incredibly precise, because deviations to alignment in the nanometer regime can lead to things like a loss of device yield or shorting of devices, or even if you get a wire too close to another, you can start to lead to device variability or hot spots in your devices where there may be some thermal migration or increases in local thermal temperatures that can cost you performance. So having more processes that are self-aligning is something that I think may impact our ability to make these devices in the future.
Is there anything else disrupting at the horizon that you can share? Or is there anything upcoming that is particularly revolutionary in the work that you guys are doing over there?
One area, and I won't go into the exact specifics, but that notion, that thesis of rethinking materials in general is one that we're exploiting for materials in the electronics applications. And if you think about it now, the conventional perspective on materials is generally as structural materials. So if you look around your room right now, or if you think about the materials that you use that are plastic or that are polymers, in those type of materials, every effort is made to minimize bonds from breaking. And that's sort of a traditional notion of how people have thought about making new materials. In this idea of using a dynamic bond, it's the exact opposite. It's being able to break and reform bonds reversibly. And you can do that with these dynamic covalent type of units like disulfides that will undergo disulfide metathesis when they're exposed to light, or Diels-Alder chemistry that will undergo reversible reactions, retro-Diels-Alder reactions at elevated temperatures. And if you put those in a material, you can achieve a spectrum of different types of macroscopic properties. So for instance, you can make things like shape memory polymers. You can make self-healing materials. So if I have a polymeric material, I can scratch it or I can break it and then mend it back together. And even that sounds simple, but that's very difficult to achieve with your conventional polymers. I mean, if you break a bottle, you're not going to put it back together. So using that type of process of being able to break and reversibly reform bonds is very useful. And I think it has a number of different types of applications for electronics, some of which may be in packaging materials, some of it may be in these selective depositions. I think the application in the electronics space makes a lot of sense because you can extend your ability to fabricate increasingly complex devices, whether they're modular devices for things like heterogeneous integration, or whether or not they're useful in a variety of other types of applications. I think it certainly is a very attractive perspective to use it in that.
We are coming to the end of our chat because I cannot keep you here all day, of course. There's always a final question I ask. But before going there, there's one thing I really, really have to ask. Is it really true that you invented a new method for decaffeinating coffee?
We did, and that was another story unto itself. And we were actually working on this project where we were trying to leverage what were often referred to as these solid functionalized particles to try and remove different materials from an effluent stream. So for instance, we designed a polymeric particle with a receptor that we wanted to bind specifically to molecules so that you could add this to remove impurities in oil and gas or in medical applications. So, and caffeine was a very nice model system for this and may have applications by itself. Well, none of this really worked particularly well when we tried to design a receptor specifically for caffeine, and we were looking at things like hydrogen bonding, and you can imagine designing a hydrogen bonding receptor and trying to remove caffeine from water doesn't work well, because water also is a very good hydrogen bonder. So you had a lot of competition between what you're trying to remove and the solvent that it's in at the time. So we looked at different types of platforms, like in the case that you're referring to, clay was particularly useful in binding to caffeine. And people have shown that before, but what we did a little bit differently was selectively removing caffeine and trying to leave as many of those other flavor molecules, as other components in coffee. And so what we did is we tried to find a more environmentally friendly way to go about removing caffeine and decaffeinating coffee in a selective manner to retain the taste. And so what we ended up doing is pre-treating our clay and saturating it with some of the other components in coffee. And that allowed us to remove caffeine up to, I think, 93 mole percent, as we could see it. And it was a simple solution, but it's something that worked very effectively.
It's a fascinating discussion, Rudy. Thank you very much. You work on some incredibly fascinating challenges, and you work with a lot of extremely talented people in a very stimulating environment. So, but if you had to stop and look back, what would be one piece of advice you'd pass on to a young scientist just starting in their career?
I would say that continue with science, to anyone that's interested in it and that is thinking about pursuing a career in science. We certainly need more scientists in this world to tackle some of the societal problems in general. I mean, there's a host of challenges to solve, and things like reducing the amount of greenhouse gases, in making materials more efficient. There's so many different problems to look at and solve. So I would strongly encourage anyone that's interested in science to pursue those careers. And I think it benefits community locally, as well as our society as a whole. There are so many different types of benefits that you may not even anticipate your work contributing to. And I often like to think about some of the fundamental experiments from when people studied the fundamentals of the atom. At the time, they couldn't see direct applications for any of this. They just wanted to understand why this behaved the way it did. And as a result of those fundamental experiments, we now have things like MRI that takes advantage of those fundamental concepts and understandings. And just think about that alone, the impact of having the ability to look inside people that are still alive instead of having to perform surgery. I mean, it's a huge impact that you can make, and sometimes the impact may go beyond what you could conceive of at the time. So I always think it's fascinating to see where technology goes in unanticipated directions, because you can only see so far in terms of your information in the landscape of what you think is possible. But a lot of times things happen that you wouldn't have even guessed about. So those people interested in science, please continue to pursue those careers and continue to be engaged and interested in that.
That was Dr. Rudy Wojtecki, researcher at IBM's Almaden lab and one of the Chemical and Engineering News's Talented 12. Thanks for joining us for this Season 2 episode of Bringing Chemistry to Life, and keep an ear out for more. If you enjoyed this conversation, you're sure to enjoy Dr. Wojtecki's book, video, podcast, and other content recommendations. You can download them visiting thermofisher.com/bctl, and this is also where you can request your free Bringing Chemistry to Life t-shirt. You can find the URL in the episode notes as well for a super easy access. Just check your podcast app. This episode was produced by Matt Ferris, Matthew Stock, and Emma Jean Weinstein,